Okay, so welcome to 7.4. This section covers the integration of rational functions, and we're particularly going to focus here on the method that we call partial fraction decomposition. So it's a method that allows us to integrate rational functions generally. And so our motivation here is to notice something very that, in hindsight, it's actually quite obvious. We basically have no integral formulas for rational functions, okay? So far, if we were looking at, for instance, a table of integrals, here's what we would have in terms of rational functions, so functions that are p of x over q of x. We have so far the very basic integral of 1 over x dx is equal to the natural log of absolute value of x plus c being the constant of integration. We also have the integral of 1 over x plus a dx equals the ln of absolute value of x. Actually, I should make that minus a. That makes it a little bit more general. There's historical reasons for that. But it doesn't really matter, right? The point is you modify the denominator slightly so that it's still some polynomial that's first degree, and you get ln of x minus a plus c. And you can find how to get the second formula from the first one very easily using u substitution. And we even have the integral of 1 over x raised to the n power dx is equal to 1 over n minus 1 x to the n minus 1 power plus c, given n is not 1. So as long as x isn't 1, this is just basically a modification of the power rule. And these are the three sort of integrals that we can handle so far. But if we wanted to do something like integrate or evaluate the integral of 1 over x squared plus 2x plus 1 dx, we'd be out of luck. Okay, so now let's actually talk about the method. We call this partial fraction decomposition. And the general idea is that we're going to take some rational function, which is really just, if you think about it, a fraction, and we're going to split it into simpler fractions. Okay, so here's the idea. Let f of x be written capital P of x over capital Q of x, okay, where we assume that both of these are polynomial functions of degree, whatever happens to be the degree that you want, right? So we can call the degree of the top polynomial p n, and the bottom one will have a degree m. So there are a couple of different cases that we're encounter, but we're going to assume that in each case that we have already simplified this to what we call a proper rational function, where n is less than m, okay? And why do we need this? This is related to the relationship between improper fractions and proper fractions, in that if not, we would need to perform long division first. To express it as a polynomial plus a proper rational function. In that case, we would have something that looks more like this. Some capital S of x plus some capital P prime of x over Q of x. Where now the degree of this is less than the degree of Q. This is the same Q, by the way. And this is another polynomial. All right, we won't get into all the nitty-gritty algebra of that. So for this reason, I'm going to highly recommend refresh your polynomial division. We'll see an example or two of needing to do this step first. But in general, we're going to skip right into the actual part of it. So the method of partial fraction decomposition takes this rational function p over q, or the secondary one, the p prime over q, and we're going to write it as a sum of simpler rational functions, and simpler in the denominator, okay? So there are four fundamental cases to consider. Really, we have overview of cases. Depending on the form of Q, so in other words, what kind of polynomial, what kind of factors are in Q, we're going to have four different really forms that we obtain for this, okay? So our first case, case one, is where Q is a product of distinct linear factors. So each term looks something like this, like ax plus b, okay? We'll see some examples in a second, okay? So don't worry. The point is that when we factorize Q into a product of distinct factors, these are the kinds of factors that we get, okay? Two, some repeated linear factors. So in other words, we might get something like ax plus b appearing with multiplicity 3, for instance, right? We'll call that some other, we'll give that some other power here. Let's call that r. Okay, so it'll repeat depending on what power that factor has. 3, if we have irreducible quadratic factors. And by irreducible, we mean you can't factor it further. And we're going to suppose that none of them are repeated, so they might look like ax plus bx plus c. Okay. And the fourth case, which you might expect, is the case where we have repeated quadratic factors. So basically the same case as above, but one of these factors that's quadratic has some power attached to it. All right, so you may be wondering, how come these are the only possible cases? And the answer, depending on how deep you want to get, really comes from the fundamental theorem of algebra. So background. Any polynomial, right? Any polynomial that you can think of. For instance, I'm going to write down x cubed minus 1 can be factorized uniquely into irreducible factors. So they can't be broken down into any smaller pieces. Think of this as similar to whole numbers. So any whole number similarly can be broken down into irreducible prime numbers that make them up. So we would call that the prime factorization. Every polynomial can be broken up in this way. And I'm going to try to avoid there's some nuance here that I'm purposefully avoiding, but moving forward. You know that, for instance, a difference of cubes can be broken down into the factorization x minus 1 times x squared plus x plus 1. So this would be a linear factor, and this is a irreducible quadratic factor. And it can be shown, but we won't, that any polynomial at all is going to fall into one of these cases or a combination of these cases. So you can't get an irreducible cubic factor or an irreducible fifth power factor. All of those will break down into smaller factors that are linear or quadratic, that are irreducible. Okay, so having said that, then we are going to focus on these 4 different cases one at a time. And the basic idea is whatever our polynomial is going to be. So basic idea of partial fraction decomposition, since we haven't really begun talking about what the technique is yet either. If we can think about this polynomial, p of x over q of x being integrated, this rational function being integrated, and we know that q of x is the product of some factors. So I'll just call them little q1x, little q2x, little q kx. Some of those are going to be linear, some of those are going to be quadratic. What happens to p of x, we don't really care. Then we're going to be able to take that fraction and split it up based on, into different pieces depending on one for each linear factor, possibly more. Linear or quadratic factor. So there will be a few corresponding to q1 of x, and something else will be up here, right? So we'll call that a1 of x plus a2 of x over q2 of x plus ... So we're going to be able to actually split it up the way that we want to. And this will allow us to exploit other rules that we already talked about. For instance, natural log rules, right? Power rules, and it'll allow us to actually integrate this. So we'll get into the specific details for each of these cases. Again, there are 4 distinct cases that we're going to focus on, and just be warned that these problems can be pretty hefty. They can be pretty long. Okay, so don't worry, just follow along, and then we'll get through these problems. One last thing that I should note, aside from brushing up your polynomial long division, we're going to need to solve systems of linear equations. So whatever methods or tools you have at your disposal, we're going to use those. I'm going to introduce a couple, but you're also going to be, have other tools that you can use. Keep in mind that that's not fundamentally the task here, okay? But we're going to break down a problem into something that fundamentally needs us to solve systems of linear equations. So just be prepared for that.